This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today we'll examine several illustrated examples of basic parallel DC circuit analysis. This lecture operates under the presumption the viewer has more than a passing familiarity with basic parallel DC circuit properties, including Kirchhoff's current law, and can wield the DC current divider rule without cutting themselves. If you lack this requisite level of familiarity with these topics, please review the supporting material at the Big Bad Tech channel and return to these lectures when you are so qualified. Master of parallel DC circuit analysis necessitates active participation on your part, and as such, I'm encouraging you to please pause the lecture when asked to do so and attempt the example problems on your own. If your answers do not match those illustrated, by all means feel free to rewind the lecture and correct any mistakes you may have made. Our first illustrated example features a 48-volt source in parallel with R1, a 910 ohm resistor, and R2, a 1.2 kilo ohm resistor. We're being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Before we begin the analysis of this circuit, it's perhaps worth a moment of our time to review fundamental parallel DC circuit properties. First, voltage across elements in parallel is the same. This is the most fundamental parallel circuit property. For this circuit, E equals V1, which equals V2, and they all equal 48 volts. Additionally, Kirchhoff's current law states that for any node, the summation of incoming currents equals the summation of outgoing currents. In short, what goes in must come out. A Kirchhoff's current law analysis of this parallel circuit suggests that source current equals I1 plus I2. Additionally, we should expect the smallest resistor in this parallel circuit to draw the largest amount of current and dissipate the largest amount of power. In this case, that'd be R1. Conversely, we should expect the largest resistor in this parallel circuit to draw the smallest amount of current and dissipate the least amount of power. In this case, R2. Finally, power in always equals power out. For this circuit, power total equals P1 plus P2. There are several ways to obtain the desired figures. Perhaps the easiest, most direct means of doing so is through the simple use of Ohm's law. I1 equals V1 over R1. Substituting our given values yields I1 to be 52.7 milliamperes. P1 equals V1 times I1. Substituting our given values yields 2.5 watts. Similarly, I2 equals V2 over R2. Substituting our given values yields 40 milliamperes, and P2 equals V2 times I2. Substituting our given values yields 1.9 watts. Source current equals I1 plus I2. Substituting our calculated values yields 92.7 milliamperes. Finally, total power equals P1 plus P2. Substituting our calculated values yields 4.5 watts. As a means of checking our work, the parallel combination of a 910 and 1.2 kilo ohm resistor yields a total resistance of 517.5 ohms. An application of Ohm's law to this simplification similarly yields a source current of 92.7 milliamperes and a total power of roughly 4.5 watts. I've got a reasonable degree of confidence our answers are correct, and we can move on to the next illustrated example. Our next illustrated example features a 24-volt source in parallel with R1, a 820 ohm resistor, R2, a 410 ohm resistor, and R3, a 750 ohm resistor. We're again being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own. If you're tracking, you should have obtained the following results. Voltage across elements in parallel is the same. For this circuit, E equals V1, which equals V2, which equals V3, and they all equal 24 volts. Kirchhoff's current law states that for any node, the summation of incoming currents equals the summation of outgoing currents. A Kirchhoff's current law analysis of this parallel circuit suggests that the source current equals I1 plus I2 plus I3. There are several ways to obtain the desired figures. Perhaps the easiest and most direct means of doing so is through use of Ohm's law and the power equations. I1 equals V1 over R1. Substituting our given values yields 29.3 milliamperes of current. P1 equals V1 times I1. Substituting our given values yields 702.4 milliwatts. Similarly, I2 equals V2 over R2. Substituting our given values yields 58.5 milliamperes. P2 equals I2 squared times R2. Substituting our given values yields 1.4 watts. Finally, I3 equals V3 over R3. Substituting our given values yields 32 milliamperes of current. P3 equals V3 squared divided by R3. Substituting our given values yields 768 milliwatts. Source current equals I1 plus I2 plus I3. Substituting our calculated values yields a source current of 119.8 milliamperes. Finally, power total equals P1 plus P2 plus P3. Substituting in our calculated values yields a total power of 2.9 watts. As a means of checking our work, these three resistors can be combined in parallel to result in a total resistance of 200.3 ohms. An application of Ohm's law solving for source current does indeed confirm that source current is 119.8 milliamperes, and total power is indeed 2.9 watts. I've got a reasonable degree of confidence our answers are correct, and we can move on to the next illustrated example. Our next illustrated example features a 50-volt source in parallel with R1, a 1 kilo ohm resistor, and R2, a 1.4 kilo ohm resistor. We're again being asked to solve for the voltage drop across each element, the current through each element, the power dissipated by each element, the source current, and the total power. By all means, pause the lecture and try this on your own.